How the frack does this show you the structure of DNA? So this is photo 51, and it is a fiber X-ray diffraction image of DNA. It was taken by Raymond Gosling, who was a graduate student in Rosalind Franklin's lab in the 1950s, and this and other of their images were used by Francis Crick and James Watson to solve the structure of DNA. There's a lot of information that you can get from this image, including the fact that it's a double helix, including the fact that it's like the spacing of the base pairs, the fact that the phosphates are on the outside, the bases are in the inside, how like the pitch, the turn, all of these various things. And so let's take a look at how we can like read this. So get more into the difference between like fiber diffraction and crystal diffraction. So I am more familiar with crystal diffraction, so like X-ray crystallography, but the principles are fairly similar. They're just kind of different in ways that can confuse your brain. A key concept that you need to know is that what we're going to be looking at, the signals we're going to be seeing, are going to be coming from wave interference. So basically, X-rays are really energetic light waves, and they can add together, which we call constructive interference, or they can cancel each other out, which we call destructive interference. There are specific like geometries and distances and stuff that'll make it so that they build together. And we call this diffraction, when they have this pattern where they like they all add together constructively to give you a stronger signal. And then in other places, they're all canceling each other out. Because this can only occur with specific like geometries, by seeing where we get a diffraction pattern, so where we get signal, we can work backwards and kind of get information about the geometry of the molecule or the thing that was producing that signal. The second important thing to know is that we're going to be dealing with reciprocal space. So things that are really close together in real space, so like in reality, are going to be farther apart in the diffraction pattern that we see, and things that are farther apart in reality in real space are going to be closer together in the pattern that we see. So basically we need a source of those waves though to have those like spacings. And so in X-ray diffraction, what you use is you have X-rays, which are really energetic light waves. And what's going to happen is that the atoms, the electrons in the atoms, are actually going to interact with those X-rays, and they're going to scatter them. And then it's these scattered waves that are going to interact. So you might have done some sort of like optical physics experiment in like a physics class where you're using slits, and then you're sending light waves through those slits. You're getting diffraction through these slits. What's happening in our molecular X-ray diffraction is that instead of slits, what we have is the atoms are actually serving as sources of these waves of scattering. And then it's these scattered waves that are going to be interacting with one another. In order to get diffraction to happen, so in order to get it so that you have these waves being like in phase and completely building together, and then in these specific places to give you a signal and then canceling out everywhere else, what has to happen is you have to have some sort of regular spacing of the sources, so of the scatterers. And so in one way to do this is crystallography, where basically what you do is you get the molecule to actually form these crystals, and where you have you have this symmetry throughout, because it's kind of like a brick wall. And so you have this symmetry through crystallography. So through the arrangement of these molecules being arranged in the exact same way throughout the crystal. In fiber diffraction, you still need to have symmetry, but the symmetry, instead of coming from the molecules like being spaced in a certain way, the symmetry is coming from the molecules themselves. And so they have this axis of symmetry, this fiber axis. So in DNA, this is the axis going like down through the double helix. And so if you arrange these all the DNA strands, so if you like pull them between glass rods so that they're all arranged along their axis, then because they have this symmetry around them, even though it's kind of like, if you like, you can move them up or down or whatever,
But because the symmetry, they're all along the same axis of symmetry, what happens is that you can get this this repeating spacing of the units that then give you information. It's not quite as much information as you would get from like crystallography, but you can still get information about the geometry because it's the inherent geometry of these molecules that is giving them this regular spacing that is going to allow them to produce those diffraction signals, diffraction pattern. And because that can only occur with certain geometries, you can measure the distances in this diffraction pattern you get and get information about the molecule itself. If we imagine the helix as like two series of planes, so you have this one series that's going like this green series, and then this red series that's going like this. Then what we can see is that we can either think of this kind of like in the crystallography term when we're thinking about like Bragg's law, or we can, and like the waves bouncing off kind of, or we can think of it in terms of being like two series of slits. So you have a series of slits this way, and then you have a series of slits this way. This is for a single helix. And if you were to do this with a single helix, what you would get would be, you would have a pattern of spotted lines going like this, kind of like you see here. But what you'll also see here, we'll get into more about how we can learn about the distance between these lines. But what we can see is that we're missing this line. This is like the fourth, the layer 4, blend layer 4. And because we're missing this, this is actually telling us that instead of just having a single helix, so this would be like a single helix, but what we actually have is we have a double helix. So we have a second, so it's like we have two of these. So we'd have another line like right below this and another line right below this. And this is what tells you that you have the second strand, and you have this strand at an offset. And so basically this offset is making it so that you have this strand that's, it's like has the same like repeat, like, but it has the same pitch. So it has like the same distance between its lines, but it's offset such that you have it continue like regularly, exactly out of step, exactly out of phase with the other set of planes, and so it's canceling it out. So it has to be at this like regular space pattern, so they're happening at the same, like they have the same pitch, they have the same distance between like one turn and the next, but they have this shift that's at this fraction that's going to make it so that they completely cancel out. Basically, if you do some geometry, you can figure out that there's only a few different fractions of the wavelength that would actually give you this value. And biologically, like only one of them would make sense, which would be a 3/8 of the pitch. So a key thing to know about diffraction, so whether it's from a crystal, whether it's from a fiber, or anything, is that what we're dealing with is we're going to be dealing with reciprocal space. So in reciprocal space, things that are little in real space, so in like reality, things that are really close together are going to be far apart in reciprocal space, and things that are far apart in reciprocal space are going to be close together in real space. So we're talking about reciprocal, like 1 over this. So 1 over a bigger number is going to be a smaller number than 1 over a smaller number. So when you're looking at this structure, it's kind of, you might think like, oh, okay, so these close together lines are going to correspond to the bases. No, they don't. These are going to correspond to the pitch. So these are going to correspond to the distance between, like, from one turn to the next. And so the smallest, this is like the bigger repeating pattern, the bigger like repeating unit in the real space, so in the DNA, is going to be this pitch, and it's going to correspond to the smaller repeating unit in the reciprocal space in our diffraction pattern. It's actually this bigger line, so between this equatorial axis and this like meridian arch thing, this is actually going to be, this bigger distance is going to tell us about the distance between the closer together repeating parts. So between the bases. So this information from here to here, this is going to give us information about the H, about the distance between the bases, like on top, like from one to the next. And since it's reciprocal space, it's going to be 1 over H. So when they went and they measured out this distance, and then they took like the reciprocal of it, they found that the height, so that they found that H, so the distance between the bases, was 3.4 angstroms. So an angstrom is just it's 0.1 nanometer. So a nanometer is a billionth of a meter. So we're talking about really small distances. And we're talking about a smaller distance than we're talking about with our pitch, which is the distance from like one turn to the next. And so when we're talking about the interbase distance, we're talking about going from this equatorial axis to like this top of this arc. When we want to get information about the pitch, we're going to be wanting to look at these layer lines, so these closer together spaced ones. And the distance between these layer lines is going to be 1 over P. And so when they were able to measure that, they could find out that this pitch was going to be 34 angstrom. So if you take 34 angstroms, so we know we have to go 34 angstroms per turn, and we have an interbase distance of 3.4. This is how we figure out that we have 10 bases per turn. Okay, so we have the number per term and we have the pitch. We still need to figure out the radius. So like the radius of our helix. And for this, we actually look at this angle, the angle of our X. So like this angle. And so this is actually going to be, because we're in like reciprocal space, this is going to be, this angle here is kind of going to be, now it's vertical. So it's this angle. So they can measure this angle in their diffraction image. And here they have to do a little bit of trig. And so they have, they find that this angle is 40 degrees. And then they use the trig relationship that the tan of the angle equals P over 4R. And then they're able to calculate that R is 34 angstrom divided by 4 tan 40 degrees equals 10 angstrom. So it's a nanometer. Yeah, I don't really do math. But anyway, I haven't done like trig in a long time. But they so the basic idea is that you have figure out that this radius is going to be a nanometer. And so now you have all of this information about like the geometry of the geometry of this helix. And we have the information that we have the double helix with this offset of 3/8, thanks to the missing fourth layer line. The pitch was 34 angstroms. So if you take 3/8 of 34 angstroms, you get a shift of 12.75 angstroms. So this is telling you the offset between the two strands. And because you have this offset, this is what's going to give us the major groove and the minor groove of the DNA. So now let's talk about a couple other things we can learn from this. So you can see we kind of have like this missing, we have like this blank space in these like rhomboids. And this is actually helping tell them that the phosphates were on the outside. So there have been some people thinking that the phosphates were on the inside. And the bases were sticking out, which would make it easier to read, but it would also put all this negatively charged phosphates closer together. We would put those hydrophobic bases out on the outside. So yeah, that wouldn't work very well. And instead we have the information can be read out in those major, in the major groove and stuff. But anyway, this is helping show that the phosphates were on the outside, and the phosphates are going to be what's going to give us the most scattering of the electrons, because the most scattering of the X-rays, because the phosphorus atoms are bigger and they have more electrons than the stuff like in the center. But anyway, so that's will give them that information. And then we can also get information from we can also get information from these big smears, these like meridian smears at the top and the bottom. And so remember, these smears, this big distance is corresponding to the smaller distance between the interbase distance. So between as you're going up, like the stair, like if you were to think of like a helical staircase, it'd be like the stair height. And so this is going to be, that will be the 1/h. But the fact that you see this smear at all is actually informative, because it's telling you that the bases are fairly horizontal. So when we're thinking of the double helix, when the X-ray is hitting it like perpendicular to this fiber axis, so it's heading it like straight on type of thing. If it's hitting if all of the bases were not horizontal, because you have these like 4 different bases, they would all kind of like, the signals would all kind of like wash each other out. But they all look pretty similar when you're looking at them like straight on, if you're hitting them straight on. And so the fact that we can see this is telling us that they're not just, the signals aren't all just like canceling each other out. And so we get the signal at the top and at the bottom in these smears. And note that a lot of this I'm like grossly oversimplifying, but if you try to dig too deep into the physics, then your brain really hurts. But I will give some sources and stuff, some good sites if people are interested in more. So the fact that we can see them is telling us that they're fairly horizontal, but the fact that they're in this arc is telling us that they're not quite horizontal. And so in fact, there's a little bit of a pitch in the bases. And they're actually kind of pitched so that what it does is it kind of gives the helix, it not only like gives the helix its form, but it kind of helps maximize the favorable interactions between the bases and like the pi stacking interactions that we talked about in yesterday's video. What's really interesting is that the information about the fact that the strands were anti-parallel, so that one strand was running in one direction, one strand was running in the other direction. This information actually came from X-ray, or at least semi-crystalline, from crystalline or at least semi-crystalline forms of DNA. So this is the pattern of A-form DNA. So A-form is kind of like the squatter form of DNA. And so when it was actually kind of part of the key of getting this double helix, getting this strong structure, all this information, was that they were able to figure out a way to get the DNA to diffract in the fiber form. And so they had to do things to try to get it like the optimal amount of wetness kind of thing. So in a crystal, basically everything is kind of like all stuck together in this like stiff solid type of thing. Whereas in the fibers, they're more like, these are like wetter kind of, so they had to do things like controlling humidity and this tight chambers and all of this really cool stuff. That was a lot of work, I'm sure. But having this like wet form was really important for getting this fiber pattern. When they were trying to do stuff before, when they were doing, like they were getting some like crystalline or at least semi-crystalline, where you kind of had like crystals of DNA that were kind of oriented, kind of fiber-like, various things. So you can see that when you have like in this, you're actually seeing diffraction spots kind of like interfering with this like fiber diffraction pattern. So these are more like what we see when we do like X-ray crystallography, where we have like a distinct pattern of spots rather than like layer lines and stuff. But because they had this more like crystal structure, this actually gave you information about, this gave Crick the information that he needed in order to know that it was, the strands were anti-parallel, because you could only basically get the form of symmetry that they saw if the strands were anti-parallel. So they found that it crystallized with like a twofold symmetry perpendicular to like the backbone axis. And so when Crick saw this, he knew that this would mean that this strand must be anti-parallel, because that's the only way that you could get that form of symmetry. So although this is a fiber diffraction picture and it gave us most of the information, they also got information from the more crystalline forms. You can also see that with the A form, you don't get quite as strong of like the meridian arch. In the A form, the pitch is going to shrink by about 20%. So the distance like between your curves is going to be, now it's going to be like 2.8. Then it's going to be about like 2.8 angstrom, so about 20. So it's going to be about 28 angstrom, or like 2.8 nanometers for the aDNA compared to the 34 angstroms, or 3.4 nanometers for the B DNA. So the B DNAs are like main form of DNA. What happens with the aDNA is it's kind of like you squish it down more. So you're actually going to have like 11 nucleotides per turn though, even though you are squishing it down. So even though this pitch is shorter, it's actually going to have another base in there. And so you're actually going to have 11 bases per turn instead of 10. And so they're going to adopt like a 20-degree tilt, and basically this will make it so that only 2 of the bases per the turn are kind of like hit edge on by the X-rays, and so you don't get quite as strong of the meridian arcs. So this is where photo 51 was published in April 1953 in Nature, the journal Nature. It was actually in the same article as Watson and Crick's, the same issue as Watson and Crick's famous paper, but unfortunately it got less attention.
So you kind of go from hearing people like leave out Rosalind Franklin, and you're like, give Rosalind Franklin credit, and then you're a grad student, and then you're like, hey, the grad student actually took the picture, give Raymond Gosling some credit. And then you get really, really ungrateful, and then when people are like crediting them both, but then they're calling it like a crystal image, you're like, no, it's actually a fiber diffraction image, but thank you for crediting them. And then you get really into learning how it works.
So I hope that helped and didn't just confuse you more. Yeah, it can get kind of confusing, and I hope I explained it in a way that can help make it clearer for you.